A single photon can land on a detector as one tiny point, one flash, one place, one recorded event. Ordinary intuition expects the picture to be simple. A small piece of the light leaves the source, passes through one of two openings, travels along a path, and ends where that path takes it. But when enough of these single impacts are collected, they do not form two simple bands behind the two openings. They form alternating bright and dark stripes, the signature of interference. As if each photon did not simply choose one route, but allowed two possible routes to overlap before becoming one result. Then one physical change destroys the pattern. Add a detector that can reveal which opening the photon passed through. Not a human eye, not a mind deciding to look, just a device that can leave a record of the path. When that path information becomes available, the interference disappears. The dark bands are no longer protected by wave cancellation. The light begins to behave the way ordinary intuition wanted it to behave from the beginning. Like individual particles passing through one opening or the other. This is not a poetic mismatch, it is a physical one. Without a deeper mechanism, the basic idea of a microscopic object carrying a ready-made path before measurement would fail. We would have to explain why one impact looks particle-like, why many impacts together carry a wave pattern, and why the mere availability of path information is enough to erase that wave pattern. The problem begins with measurement itself, not as passive looking, but as an interaction that forces a field of possibilities into a recordable event. In daily life, nothing prepares us for this. A room in darkness still feels like a room. A window remains in the wall. A book remains on the table. The floor does not dissolve when the lights go out, and the door does not lose its position because no one is watching it. The ordinary world seems to possess its properties whether or not we inspect them. Location, shape, mass, speed, temperature, and distance appear to belong to objects in a stable way, waiting only to be discovered. This intuition is not foolish. It is the reason the body can move confidently through the world. We leave a cup on a kitchen counter and return to it later. We step toward a staircase because we expect its steps to remain where they were. We cross a street because cars follow continuous paths, not sudden appearances. If the familiar world did not behave with this practical stability, ordinary action would become impossible. The nervous system depends on a classical world, even before the mind names it as one. Physics honoured that intuition for centuries because it worked. A stone thrown through the air follows a path. A pendulum swings through a predictable arc. The moon does not need a witness to continue orbiting Earth. A train that disappears behind trees does not become a cloud of possible trains. The unseen part of its motion remains part of the same continuous account. Classical physics gave that account equations, and those equations became one of the most powerful achievements in human thought. In the classical view, uncertainty belongs mostly to us. A ball has a position and velocity even if we do not measure them perfectly. A raindrop has a path even if no one tracks each turn of its fall. A spinning coin may be hard to predict, but the difficulty comes from missing details, the exact force of the thumb, the air currents, the angle of impact, the roughness of the surface. The world is treated as definite underneath our ignorance. If we knew enough, the hidden account could, in principle, be uncovered. Quantum physics did not reject this picture because it was useless. It rejected it at the smaller scales because experiments forced the issue. With photons, electrons, atoms, and other quantum systems, some questions cannot be asked in the old way. Not because instruments are weak, not because nature is playing a trick. The problem is sharper. Before a certain kind of measurement, some properties may not be determined in the same way a classical object's properties are determined. A photon's path is not always like a thin line drawn secretly through space. An electron's position is not always like an address written on an envelope. The quantum state is described by a mathematical structure that gives possible outcomes and their probabilities, not by a single hidden miniature picture waiting to be enlarged. Measurement is therefore not just reading a label, it is a physical event in which the system, the apparatus, and sometimes the surrounding environment become linked to one recorded result. The word observation can mislead us here. In ordinary language, observation means looking. It suggests an eye, a mind, a person noticing something. In quantum physics, the crucial thing is not the psychology of a viewer. It is the existence of an interaction that makes information available. A detector can record a path while no person is in the room. A photographic plate can be marked. An atom can be excited. An electronic signal can be stored. The human observer may arrive later. The quantum system has already met the measuring world. That distinction matters because the real mystery is not that consciousness magically controls matter. The real mystery is stranger and cleaner. Microscopic systems behave differently depending on what kind of information the experiment physically allows to exist. If the setup preserves the indistinguishability of alternatives, wave-like interference appears. If the setup marks the alternatives so that they can be told apart, the interference is lost. The difference is not a change in human curiosity. It is a change in the physical conditions under which possibilities can combine. The double-slit experiment is the clearest doorway into this problem, because it is almost embarrassingly simple. A source sends light toward a barrier. The barrier has two narrow openings. Behind it waits a detecting screen. At first, this sounds like a problem from ordinary optics. Open one slit and light passes through. Open the other and light passes through there. Open both, and common sense expects the two results to add. More openings should mean more light, perhaps two bright patches. One behind each slit. That is what classical particles would do. Imagine tiny grains fired toward the barrier. Most strike the wall and stop. Some pass through the left opening, others pass through the right. Behind the barrier, two regions of impact appear. The pattern may blur because the grains scatter at angles, but the logic remains simple. Each grain travels through one opening. The final pattern is the sum of grains that went left and grains that went right. Two routes produce two collections of impacts. Waves behave differently. When a water wave reaches two narrow gaps, each gap becomes a source of spreading ripples. These ripples overlap. Where crest meets crest, the wave grows stronger. Where crest meets trough, the motion weakens or cancels. This is interference, and it is not mysterious in water because the wave is extended. It can pass through both gaps, overlap with itself, and create a pattern of alternating reinforcement and cancellation. Light too produces an interference pattern behind two slits. Instead of two simple bright regions, the screen shows a series of bright and dark bands. The bright bands appear where the wave contributions reinforce one another. The dark bands appear where they cancel. The spacing depends on the wavelength of the light, the distance between the slits, and the distance to the screen. The pattern is not decoration. It is the geometry of wave overlap made visible. If light were only a classical wave, the picture might end there, but light also arrives in packets. Detectors do not register a smooth smear of energy spread across the whole screen. They register discrete events. A click, a tiny mark, a localized absorption. One photon is detected here, another there. The energy of light is exchanged in individual quanta. The thing that travels like a wave is recorded like a particle. This creates a sharp contradiction. If a photon is a particle, why does the accumulated pattern contain interference? If it is a wave, why does each detection happen at one point? Classical language wants one answer. Quantum physics gives a more difficult one. The same system can require wave-like mathematics before detection and particle-like records at detection. The experiment does not allow us to choose the picture we prefer. It forces both pictures into the same apparatus. The contradiction becomes impossible to ignore when the source is dimmed so that photons pass through the experiment one at a time. There is no crowd of photons moving together, no ordinary light wave made of many simultaneous particles interfering with itself as a group. The detector waits. One photon is emitted. One mark appears. Then another photon is emitted. Another mark appears. At first, the point seems scattered without pattern. But as the marks accumulate, order emerges. Dozens become hundreds. Hundreds become thousands. Thousands become a banded structure. The interference pattern slowly appears from individual impacts, as if each photon had somehow been guided by the availability of both slits. No single impact shows the whole pattern. Each event is local, yet the distribution of many local events reveals wave-like interference. This is the moment when the ordinary idea of path begins to lose its footing. A classical particle can go through the left slit or the right slit. If we do not know which, that is our ignorance. But if photons were merely divided into two hidden groups, one group passing left and the other passing right, the final pattern would be the sum of two single slit patterns. It would not contain the full interference structure. The dark bands would not appear in the same way. Something about the coexistence of alternatives affects the probabilities of detection. Quantum theory describes this using probability amplitudes. An amplitude is not an ordinary probability. It has a wave-like character, including a phase, so amplitudes associated with different alternatives can add or cancel. Only after combining these amplitudes do we calculate the probabilities for actual results. That is why the screen receives individual dots, yet the dots build a wave pattern. The wave is not a spread-out cloud of ordinary energy arriving everywhere at once. It is a structure in the mathematics of possible outcomes. The photon is not usefully pictured as a tiny ball split into two half-balls. It is not a conscious traveller choosing a route. The more careful statement is that, when the experiment contains no information that distinguishes the two paths, the quantum state evolves as a superposition of path alternatives. Those alternatives contribute amplitudes to the final detection probabilities. Because amplitudes can interfere, some outcomes become more likely and others are suppressed. This is different from not knowing which shell hides a bead. In that case, the bead is under one shell all along. The probability describes ignorance about a definite situation. In the double-slit experiment, the interference pattern shows that the alternatives are not merely hidden classical facts. The possibilities behave as if they have physical consequences before one of them becomes part of a recorded event. This is why quantum uncertainty is not just ordinary secrecy. A dark band on the screen is especially revealing. It is not just a place where light happened not to land. It is a place where, under the wave calculation, the contributions from the two paths cancel. If one slit is closed, photons can arrive in regions that become dark when the second slit is opened. Opening an additional path can reduce the probability of detection at some points. That result is deeply non-classical. In the particle picture, giving a photon another possible route should not remove arrivals that were possible before. In the quantum picture, the second route changes the amplitude structure of the whole experiment. This is a quiet but severe physical consequence. Possibility itself has structure. The set of available alternatives is not just a list of hidden options, it affects what can later become actual. A photon recorded as one point has still obeyed a probability pattern shaped by more than one possible path. The final result is definite, but the route to that definiteness is not a classical route. The double-slit experiment therefore does not simply show that light is sometimes a wave and sometimes a particle. That phrase is too comfortable. It suggests light has two costumes and chooses one depending on the stage. The deeper fact is that classical categories are incomplete. The quantum system is described by a state whose evolution can produce interference, while measurement produces definite localized outcomes. Wave and particle are not two secret identities. They are two limited classical languages forced to describe something that is neither in the old sense. The familiar world gives us objects with paths because the familiar world is large, warm, noisy, and constantly interacting with its surroundings. Dust grains scatter light, air molecules collide with surfaces, warm objects radiate photons, tables, books, and windows are never isolated from their environment. Their microscopic quantum possibilities become entangled with countless external degrees of freedom so quickly that ordinary interference between visibly different histories is not accessible. That is why the book on the table behaves like a book, not like a lone photon moving through a protected apparatus. But at the scale of a carefully isolated photon, the world has not yet become that noisy classical record. The alternatives can remain coherent. They can preserve the phase relationships needed for interference. The experiment is not showing us that everyday reality is fake. It is showing us that everyday definiteness is not the deepest starting point. It is an achievement of scale, interaction, and recording. This gives the two slits their power. They do not merely split light, they split intuition. On one side stands the classical expectation: a thing has a path, whether or not we know it. On the other stands the quantum result: if the paths remain physically indistinguishable, the experiment behaves as if both alternatives contribute to the outcome. The question is no longer only where the photon went. The question is whether where it went is even a well-formed classical question before the experiment makes path information real. The temptation is to imagine a tiny hidden account. Perhaps the photon really went through one slit, but a mysterious wave went through both and guided it. Perhaps the photon somehow sampled both routes. Perhaps it took every possible path in a mathematical sense. Different interpretations of quantum theory offer different ways to speak about what is happening beneath the predictions. But the experimental fact that matters for this first layer is simpler. When which path information is absent, interference appears. When which path information is present, interference disappears. To see why this is not just a matter of disturbance, imagine trying to peek gently. In classical physics, a measurement may disturb a system because the measuring device is clumsy. Shine light on a tiny object, and the light may push it. Touch a thermometer to a small drop of water, and the thermometer may alter the temperature slightly. But this is a practical weakness. One can dream of better instruments, softer probes, less invasive methods. The property itself is assumed to have been there. In the double-slit experiment, the issue is not simply that a detector bumps the photon too hard. The deeper condition is distinguishability. If the world contains information that can tell the paths apart, the interference pattern is lost. The path alternatives no longer combine in the same way. The experiment has been changed from one that preserves coherent alternatives to one that marks them. It is the physical availability of path information that matters. A witch path detector does not have to be dramatic. It only has to correlate some record with the path taken. One state of the detector means left, another means right. Once that correlation exists, the two alternatives are no longer indistinguishable within the full physical setup. The photon's path has become linked to another system. The delicate phase relationship that allowed the alternatives to interfere is no longer available in the same way for the final screen pattern. The shift is decisive. Measurement is not an afterthought added to a completed microscopic account. It helps define which kind of account can be told. If the apparatus is arranged to preserve ambiguity, the statistics reveal interference. If the apparatus is arranged to extract path information, the statistics lose it. The photon does not simply carry all classical answers at once and wait for us to reveal the one we ask for. The possible answers depend on the physical question the experiment is built to ask. The old picture of observation as passive seeing cannot survive this. In a classical world, measurement ideally uncovers what was already the case. The train had a speed before the radar measured it. The planet had a position before the telescope recorded it. The coin had a face after landing even if no one had looked yet. But in the quantum world, at least for some properties, measurement is tied to the conditions under which the property becomes definite enough to record. This does not mean anything can happen. Quantum mechanics is not a theory of unlimited freedom. It gives precise probabilities. It predicts interference patterns. It predicts how the pattern changes if the wavelength changes, if the slit separation changes, if detectors are added, or if path information is erased before it becomes available. The theory is not vague. What is difficult is not the calculation. What is difficult is the image of reality that the calculation permits. The detector screen is brutally concrete. It never shows a half-detected photon smeared across several bands. It shows one point at a time. Laboratory records are made of definite events. A counter clicks or does not click. A pixel fires or does not fire. An atom is found in one state or another. The quantum state may encode several possible outcomes, but the apparatus gives one result in a single run. Yet the collection of these single results carries the memory of possibilities that were never individually recorded. The interference pattern is a fossil of alternatives. It tells us that the final dots cannot be explained by pretending each photon followed one ordinary hidden route through one ordinary slit. The pattern is made of actual impacts but shaped by unrealized paths. That is the quiet violence quantum theory does to classical thought. It makes the unrealized physically relevant without making it directly observable. A useful metaphor is a night harbour seen through fog. From a distance, only the final lights on the water are visible, one here, one there. If each light were a boat following a marked channel, we could reconstruct simple routes behind them. But the pattern of arrivals carries signs of currents that no single boat reveals. The metaphor has limits. A photon is not a boat, and probability amplitudes are not water currents, but it captures one part of the unease. The visible record is definite, while the conditions shaping it are not classical trajectories. The real apparatus is cleaner than the metaphor. The slits define possible alternatives. The source prepares photons, the screen records localized events, the mathematics assigns amplitudes. The experimenter changes where the path information exists. The result changes accordingly. Each piece has a physical role. The mystery does not come from darkness or vagueness. It comes from the fact that the roles cannot be rearranged into the old account without losing the pattern. The question of which slit did it really pass through is therefore not always like asking which road a traveller took. Sometimes the correct answer is that the experiment was not set up to make that distinction real. If one insists that a definite path existed anyway, hidden behind the experiment one must explain why the probabilities show interference. If one measures the path, one gets the path, but loses the interference. Quantum mechanics does not let both classical pictures appear in the same arrangement. This is sometimes called complementarity. Certain experimental arrangements reveal wave-like interference. Others reveal particle-like path information. The two descriptions are both necessary, but not simultaneously available in the same classical sense. The more clearly the path is marked, the less interference remains. The more clearly interference is preserved, the less path information can exist. Nature does not merely hide one answer while showing another. The conditions for the two kinds of answer interfere with each other. Complementarity is not a slogan meant to stop questions. It is a statement about the structure of experiments. A measurement that answers one question may physically prevent the pattern that would answer another. The apparatus is not just a window, it is part of the phenomenon being defined. This is why quantum physics forced physicists to talk not only about objects, but about experimental conditions. For a long time, classical physics could treat measurement as a minor inconvenience. The world had its state. The experimenter tried to learn it without disturbing it too much. Quantum physics made that separation unstable. When a photon meets a double-slit apparatus, the difference between having path information and not having it is not a detail after the fact. It decides whether the final statistics belong to a wave-like interference pattern or a particle-like sum. This is why the language of the observer became famous, and why it caused so much confusion. The observer in quantum mechanics is not primarily a person staring into the darkness. The observer is any physical arrangement that makes a result definite enough to be recorded. A detector near a slit, a screen absorbing a photon, an atom carrying path information, an environment scattering information away, all of these can function as parts of observation in the relevant physical sense. The eye is late, the record is early. If a witch path detector is present but no one checks its output, the interference is still destroyed if the path information has been physically recorded. The universe does not wait for a human to become curious. A recordable correlation is enough. That is one of the most important safeguards against a misleading mystical reading. Quantum theory gives observation a deep role, but observation means physical interaction, not conscious wishing. Still, removing consciousness from the explanation does not make the phenomenon ordinary, it makes it more precise. The disturbing fact remains. The availability of information changes which phenomena can occur. Information here is not an abstract note in a notebook. It is information carried by physical states. If the path is marked, the full system contains a difference between left and right. If no such mark exists, the alternatives can remain coherent and interfere. The world does not merely contain facts, it contains conditions under which facts can become defined. This point reaches into the foundations of physics because it changes what we mean by a property. In classical thinking, a property belongs to an object whether or not we ask about it. Measurement reveals the value. In the quantum case, some properties are tied to measurement contexts. A photon can be detected at one place, but the probability of that place may depend on a superposition of alternatives that cannot be translated into one prior path. The property becomes sharp at the point of interaction, while the prior description remains a map of possibilities. The word map is useful if it is handled carefully. A road map shows roads that exist whether or not we travel them. A quantum state is not like that. It is a mathematical object used to generate probabilities for possible measurement outcomes. In the double-slit experiment, it includes the contribution associated with both slits. But it does not give a simple little movie of a photon moving through space. It gives the structure from which the distribution of future records can be predicted. This is why one photon at a time can still build a pattern. Each photon is detected once. The distribution over many repetitions is governed by the same quantum state prepared in the same way. Quantum physics is statistical without being merely disorderly. It cannot tell us where a single photon must land, but it can tell us how many land in each region after repeated trials. The result is a strange combination: individual unpredictability and collective precision. That combination already tells us that the old deterministic machine has failed at the microscopic level, not because the world has become lawless. The laws are exact. The wave equation evolves with precision. The probability rule is exact in its domain. Experiments repeat. Technology depends on these rules. But the law does not always give a single individual outcome. It gives a structure of possible outcomes and the probabilities with which records appear. The double-slit experiment condenses that entire shift into one visible pattern. A photon leaves no continuous glowing trail. No tiny marker shows both paths. No screen displays the wave function itself. What we see are points. But the points arrange themselves according to a rule that ordinary particles cannot obey. Then, when we demand the path, the rule changes. The same photon source, the same slits, the same screen. But a different information structure produces a different kind of the world on the detector. The problem becomes most disciplined here. Measurement does not create reality from imagination. It does not require a human mind to summon particles into existence. It does something more physically exact. It changes the relation between alternatives, information, and outcomes. A quantum system that could display interference loses that ability when its alternatives become distinguishable. The act of knowing a path has a cost in the pattern of possible results. The cost is not emotional. It is not philosophical decoration. It is visible on the screen. The dark bands fill in. The bright bands lose contrast. The delicate sign of overlapping possibilities disappears. A single piece of information, left or right, can erase the wave-like distribution that would otherwise emerge from thousands of individual impacts. The universe has not become less lawful. It has changed which law-shaped pattern can appear. The familiar room returns in a different light. The book, the window, the wall, and the floor do not behave like isolated photons because they are constantly being measured by their surroundings. Light scatters from them, air touches them, heat leaks from them. Their positions are redundantly recorded in the environment. They are not waiting for human observation to become real. They are entangled with a world that has already made their macroscopic alternatives practically distinguishable. That is why our classical intuition works so well. It was trained inside a world where enormous numbers of interactions continually stabilize records. We do not notice this because it never stops. The environment is a silent witness, not in a conscious sense, but in a physical one. It carries away information about objects all the time. A chair is visible because photons have scattered from it. A sound is heard because pressure waves have travelled through air. A footprint remains because material has been displaced. The ordinary world is full of traces. The quantum experiment is powerful because it removes those traces as much as possible. It protects the alternatives from being marked too early. It creates a small region where the old classical demand for a definite path can be suspended long enough for interference to appear. Then it shows how easily the pattern is lost when a record is introduced. The experiment is not a trick. It is a controlled absence of ordinary leakage. In that absence, the microscopic world shows what the macroscopic world usually hides. Before a record, the useful description is not a hidden path, but a coherent structure of possibilities. After a record, the result is definite. Between those statements lies the problem that will not go away. The theory predicts the pattern. The detector records one event. The apparatus decides which question is physically asked. The old idea that reality simply possesses every classical answer before measurement no longer fits. This shift is not the end of the measurement problem. It is the place where the problem becomes unavoidable. If measuring a path destroys interference, then measurement is not just an act of learning. If individual photons arrive as points but accumulate as waves, then particles are not little classical grains. If path information changes what pattern can exist, then information is not a passive shadow of the world. It is part of the experimental conditions that determine how the quantum world becomes a recorded result. The quiet question left by the double slit is therefore not whether the world exists when we do not look. The everyday world does, in the only sense needed for life, because it is continuously stabilized by interactions far beyond our attention. The deeper question is more exact and more difficult. When a microscopic system has several possible ways to become real in a measurement, what physically decides the single event that finally appears? In the mathematical language of quantum mechanics, the photon before measurement is not described as a tiny object carrying a fully drawn route through space. It is described by a wave function. The name is slightly dangerous, because it makes the mind imagine a physical ripple spreading through air like sound or water. The wave function is not that kind of wave. It is a mathematical object that tells physics what outcomes can appear, and how strongly each possible outcome contributes to the final statistics. In the double-slit experiment, this wave function contains the structure of both available paths. It carries the phase relationships that allow one alternative to reinforce another in some places and cancel it in others. It does not place a little photon on a secret track. It gives a map of probability amplitudes, and those amplitudes are stranger than ordinary chances. They can combine like waves before any single result is recorded. A detector, however, does not print a wave function. It does not display a cloud of possible hits. It gives one event. A pixel fires, a mark appears, a counter clicks, a photon is absorbed at one location, and the apparatus records a specific outcome. The mathematical description before measurement may contain many possible results. The physical record after measurement contains one. This transition is where one of the most famous words in quantum physics appears: collapse. Before measurement, the wave function can include a range of possible outcomes. After measurement, there is one recorded value. Physicists often say that the wave function collapses into the result that the apparatus found. The phrase is useful, but it can mislead. It sounds as if an invisible material wave literally crumpled somewhere in space. The equations themselves are more restrained. They tell us how to calculate the probabilities with extraordinary success. They do not by themselves give one universally agreed picture of what the transition means. The problem can be felt by separating two questions. The practical question is how to calculate where the photon is likely to appear. Quantum mechanics answers that question with remarkable precision. The deeper question is what the wave function actually is. Is it a real physical condition of the world, existing whether or not anyone knows it? Or is it a tool for organizing information about what can be expected from future measurements? The calculations may agree while the picture about reality changes completely. This is why the word collapse has carried so much weight. If the wave function is physically real, collapse begins to look like a real physical process. Many possibilities reduce to one actual event. If the wave function is more like a statement of knowledge, collapse may be closer to an update of information after the result is known. But the double-slit experiment prevents this from becoming a purely verbal disagreement. The presence or absence of path information changes the visible pattern. Something about the physical arrangement affects what can happen, not just what a person happens to know. The Born rule gives the bridge from wave function to statistics. In simple terms, quantum theory does not take the amplitude itself as the probability. It uses the magnitude of the amplitude to calculate the probability of a result. That detail matters because amplitudes can carry phase. They can reinforce or cancel before probabilities are obtained. Ordinary probabilities do not cancel one another in that way. If there is a 30% chance of one route and a 70% chance of another, those chances add like bookkeeping. Quantum amplitudes behave more like waves in the mathematics before they become the probabilities of records. A card lying face down on a table gives the classical contrast. The card already has a value. It may be a king, a 7, or an ace. If no one has looked, the uncertainty belongs to the players, not to the card. Turning it over reveals what was already there, but a quantum system cannot always be treated like a covered card. In some experiments, the alternatives must be allowed to interfere before a result exists in the form measurement can record. The uncertainty is not merely a lack of eyesight. The wave function, then, is less like a hidden photograph, and more like a rule for how possible records are connected. It does not show us the photon as a little bead moving through darkness. It gives the structure from which the distribution of future marks can be predicted. When measurement happens, one mark appears. The rest of the mathematical structure is no longer used in the same way for that measured system. That is the event we call collapse, whether we interpret it as a physical change, an information update, or something handled differently by another interpretation. The laboratory keeps the issue sharp. Before the measurement, the theory speaks in amplitudes. After the measurement, the apparatus speaks in records. A tiny detector does not hesitate between alternatives. It does not report that the photon almost landed in several places. It registers one outcome. The difficulty is not that physicists cannot use the theory. They can. The difficulty is that the theory uses one kind of description before measurement and another kind of fact after measurement. This tension is called the measurement problem. The name sounds technical, almost modest, but it marks a place where the quantum world touches the world of instruments, screens, notebooks, and shared facts. A photon may be described in a superposition of alternatives. A detector built from atoms that are themselves quantum systems gives a single result. If everything in the detector is also made of quantum matter, why does the detector not simply become part of an ever larger superposition? Why does it show one stable outcome rather than all possible outcomes at once? The easy answer would be to say that measuring devices are classical and photons are quantum. For many calculations, this works. We treat the small system with a wave function, and the apparatus as something that gives definite readings. That practical division helped build modern quantum physics. It allowed experiments to be designed, predictions to be tested, and technologies to be developed. But the division leaves a question behind. If the apparatus is made of atoms, and atoms obey quantum rules, why should the boundary between quantum possibility and classical fact be placed exactly where the apparatus begins? The Copenhagen tradition, associated with Niels Bohr and other architects of quantum theory, handled this boundary with caution. It emphasized that experimental outcomes must be expressed in ordinary classical terms: a spot here, a pointer there, a registered value under specified conditions. Without such classical descriptions, experimental results could not be compared or communicated. This was not a claim that measuring devices are magical. It was a discipline of language and practice. Physics must say what arrangement was built and what result was recorded. Still, the unease remains. The measuring apparatus is not outside nature. Its screen, electronics, atoms, and memory states are physical systems. If quantum mechanics is a deep theory of matter, it should not need a mysterious exemption for the equipment that measures matter. The measurement problem appears because the apparatus must be ordinary enough to show one outcome, while also being made from the same kind of quantum ingredients as the system it measures. A footprint in snow gives a careful image. Before the foot lands, there are many possible places where a mark could be made. After contact, the snow has one depression. The trace can be seen later by someone who was not present. No conscious witness was needed at the moment of formation. The analogy is imperfect because snow and boots are classical objects for this purpose, but it separates useful layers: the interaction, the physical trace, the later observer. In quantum measurement, the human eye is not the decisive first step, the trace is. The more difficult question is what counts as a trace. Is it enough that a single atom changes state depending on a photon's path? Is it enough that a stray photon scatters and carries away information? Must the information be stored in a durable apparatus? Does it matter whether anyone can ever retrieve it? These questions are not philosophical decorations. They decide whether interference remains possible. If path information leaks into the world in a way that distinguishes alternatives, the delicate amplitude relationships needed for interference can be lost. Saying that measurement is any interaction is too broad. Quantum systems interact with one another all the time, and controlled laboratory systems can still preserve superpositions when the interactions are coherent and isolated. Saying that measurement requires consciousness is too narrow. Detectors work without people watching. A record can form inside sealed equipment. The physical problem lies between these extremes. How does an interaction become the kind of record that prevents alternatives from interfering, as if they were still indistinguishable? The modern answer that explains much of this transition is decoherence. The word sounds dry, but the mechanism is concrete. Coherence means that different parts of a quantum state preserve the phase relationships that allow interference. In the double-slit experiment, the two-path amplitudes must remain coherent if they are to create bright and dark bands. Decoherence occurs when a system becomes entangled with its environment in a way that spreads information about its alternatives into many surrounding degrees of freedom. For the system we can still access, the phase relationships are effectively lost. A single photon in a carefully prepared experiment can remain coherent because the setup protects it. The apparatus is designed so that nothing in the environment learns which path was taken. The alternatives can meet again in the mathematics and interfere. But a warm object in a room is not protected. Molecules of air strike it. Thermal radiation leaves it. Light scatters from its surface. Vibrations pass through its supports. Each contact can carry away a tiny fragment of information about the object's position, motion, or state. For a large object, decoherence is overwhelmingly fast. The world around it becomes a vast recorder, not a conscious recorder, not a mind, not a witness with memory in the human sense, but a physical environment filled with correlations. The air, the light, and the surrounding matter become entangled with the object's possible states. Any visible superposition of macroscopically different positions becomes impossible to observe under ordinary conditions because the phase relationships needed for interference have dispersed into the environment. This is why a book on a shelf does not behave like a photon at two slits. Its quantum components still obey quantum laws, but the book as a macroscopic object is continuously leaking information into its surroundings. Its position is redundantly recorded by scattered photons, air molecules, and thermal radiation. The alternatives that would be visibly different for the whole book do not remain isolated long enough to interfere. The classical world is not built by human attention. It is stabilized by relentless physical contact. A delicate drawing on perfectly still water may survive for a moment. Add wind, rain, insects, floating dust, and the motion of the shore, and the fine pattern dissolves into the movement of the whole surface. Decoherence is not water, and quantum phase is not ink, but the cost is similar. A fragile relation that made a clean pattern possible becomes distributed across too many uncontrolled motions. It has not necessarily been annihilated from the complete physical description. It has become unavailable to the local experiment. This distinction matters. Decoherence does not simply say that the quantum world becomes classical because it gets messy. It says that the system becomes correlated with its environment in such a way that interference between certain alternatives becomes practically inaccessible. The total state may still be quantum, but if we look only at the system, and not at every particle of the environment that has carried away information, the system behaves like a classical mixture. The coherence has been exported beyond reach. That makes the environment a silent witness in a precise physical sense. It is not observing with awareness, it is acquiring correlations. A photon scattering from a dust grain may carry away information about where the grain was. A molecule bouncing from a surface may encode a tiny detail of position. Thermal radiation leaving an object may carry traces of its state. No one has to read these traces for them to matter. Their existence changes which interference effects remain accessible. Decoherence gives the ordinary world back to us, but not in the old way. It explains why large objects have stable classical appearances even though they are made of quantum matter. It explains why measurement devices can produce robust records. It explains why cats, books, windows and planets do not display visible superpositions in daily life. The classical world is not a separate kingdom exempt from quantum rules. It is what quantum systems look like when their phase relationships are dispersed through enormous environments. But decoherence does not close every door. It explains why interference disappears. It explains why certain sets of outcomes become stable and classical looking. It explains why, after interaction with the environment, alternatives stop behaving as if they can overlap in the way they did in the double-slit experiment. What it does not by itself explain, at least not in a way every interpretation agrees on, is why one particular outcome is the one actually recorded in a single run. Imagine a detector built to register one of two possible results. Decoherence can explain why the two possible records do not interfere with each other like waves. It can explain why a state corresponding to left and a state corresponding to right become effectively separate, stable, and resistant to recombination. But if an observer later sees left, the question remains, why this record, not the other? Decoherence turns a coherent quantum superposition into something that behaves like a set of alternatives. It does not, on its own, choose the alternative. That is not a failure of decoherence. It is a boundary of what the mechanism explains. It shows how the classical appearance of the world can emerge through interaction with the environment. It removes the need for a human mind to create definiteness. It makes measurement less like a magical jump and more like a physical spreading of information, but it still leaves the deepest measurement question under interpretation. What is the status of the other possible outcomes after a definite record appears? The old word collapse returns here, but now it is under pressure from a better mechanism. If collapse is a real physical process, decoherence may describe how the conditions for classical outcomes arise before or during that process. If collapse is only an update of information, decoherence explains why the information becomes effectively classical. If there is no collapse at all, as some interpretations propose, decoherence helps explain why different branches no longer interfere. The mechanism is widely useful because it does not depend on one philosophical picture, but it does not erase the need for a picture. The room around us becomes different under this light. Its solidity is not simple. Every surface is immersed in a storm of microscopic contacts. Photons strike walls and scatter. Air molecules collide with objects and move on. Heat radiates outward. The environment continually takes impressions from things and spreads them into the rest of the world. What feels like stillness is built from constant interaction. A table remains stable not because quantum uncertainty has vanished from nature, but because the table's macroscopically different alternatives are not protected. They are instantly entangled with the environment in ways no ordinary experiment can reverse. To recover interference between two visibly different table positions, one would need to control not only the table, but essentially every environmental trace carrying which position information. For large warm objects, that task is beyond practical possibility by an absurd margin. This is why the quantum world is easiest to reveal in isolation. Trap a single ion, send one photon through a carefully shielded path, cool a system, remove air, limit radiation, protect coherence. The more the system is separated from environmental records, the more its quantum behavior can remain visible. The more it is exposed, the more quickly it takes on the classical face of a definite object in a definite place. The double-slit experiment is therefore not a window into a ghostly unreality. It is a protected arrangement in which alternatives are allowed to remain coherent long enough to show their effect. The everyday world is the opposite, an arrangement in which alternatives are marked almost immediately by countless uncontrolled interactions. The same quantum theory underlies both. The difference lies in whether the phase relationships survive. The mechanism that destroys visible interference is also connected to one of the strangest features of quantum theory: entanglement. Decoherence happens because the system becomes entangled with the environment. To understand why this matters, the old picture of objects as independent carriers of properties has to be loosened even further. Quantum systems can share a state in a way that cannot be reduced to separate private descriptions for each part. Entanglement can arise when particles are created together or interact and then separate. After that, the complete quantum state may describe the pair as a whole, while the individual particles do not have definite values for certain properties on their own. If one particle is measured, the result is correlated with the result of measuring the other. The strength and structure of these correlations are not always explainable by saying each particle carried a hidden instruction card from the beginning. A classical comparison shows the difference. Place a red card in one envelope and a blue card in another. Send the envelopes to distant cities. When one is opened and found to contain red, the other must contain blue. Nothing mysterious has crossed the distance. The cards were fixed all along. Opening one envelope only reveals information about both. Entangled particles can produce correlations that go beyond this envelope model. The individual measurement outcomes are still random, but when many results are compared, the patterns violate limits that any simple, local, hidden instruction picture must obey. These limits are known as Bell inequalities. They are not an opinion about what feels strange. They are mathematical constraints on a world where measurement outcomes are determined by local pre-existing properties, and no influence travels faster than light. Experiments have repeatedly shown that quantum systems can violate these inequalities. That result does not mean one particle sends a usable message faster than light. It does not allow someone to control a distant outcome and communicate instantly across space. Each single result remains random. Only when the two sets of records are later compared through ordinary communication do the correlations become visible. Relativity's ban on faster-than-light signaling remains intact. But the envelope picture fails. The particles cannot be treated as if they simply carried a complete local list of answers waiting to be revealed, at least not if the theory is to remain both local in the classical sense and complete in the way the hidden card account demands. The pair has to be described by a joint quantum state. The relationship is not added after measuring, it is part of the structure of the system. Quantum theory becomes difficult to translate into ordinary speech here. If we say one particle affects the other instantly, we risk suggesting a signal that experiments do not provide. If we say nothing happens, we miss the fact that the correlations cannot be explained by classical local properties. If we say the particles are one system, we must remember they may be separated by large distances while still belonging to one mathematical state. Every phrase needs restraint because the phenomenon sits outside the habits of everyday language. The safer physical statement is narrower and stronger. Entangled systems display correlations that cannot be reproduced by any simple model in which each part carries its own preset local values for all the measurements we might choose. The whole matters. The state of the pair is not merely the sum of two independent states. Measurement reveals one result locally, but the pattern of results belongs to the pair. Einstein saw this pressure clearly. His discomfort with quantum mechanics was not a failure to understand it. He objected because the theory seemed to abandon a picture of reality in which physical properties exist locally and independently before measurement. Together with Boris Podolsky and Nathan Rosen, he helped formulate a challenge showing that if quantum mechanics were complete, then it implied a deeply non-classical structure. The aim was not to popularize weirdness. It was to test whether the theory had left something out. Bell's work later made that disagreement experimentally sharp. Instead of remaining a debate about taste, it became a question about measurable correlations. If local hidden variables existed in the simple sense, certain statistical inequalities would hold. Quantum theory predicted their violation. Experiments supported the quantum prediction. A philosophical wound became a laboratory constraint. This removes another escape route. After the double slit, one might still hope that each photon had a hidden path and that interference was somehow caused by an unseen mechanism moving alongside it. After entanglement and Bell tests, the hope for a simple local hidden variable world becomes much harder to sustain. The quantum state may be strange, but it is not an optional poetic overlay. It carries predictive content that classical local pictures cannot reproduce. The cost is conceptual. The world no longer looks like a collection of tiny independent things, each with its own complete list of properties, waiting for measurement to reveal them. Some properties appear only within a measurement context. Some correlations belong to a joint state rather than to separate parts. Some possibilities interfere until information distinguishes them, and when systems open to the environment, those delicate relations disperse into a larger web of correlations, producing the classical stability we live inside. This does not mean that everything is connected in a vague mystical sense. That phrase is too broad to be useful. Quantum entanglement is specific, mathematical, and fragile. It is created under definite physical conditions, measured through definite correlations, and often destroyed or hidden by decoherence. It cannot be used to send chosen messages faster than light. It is not evidence for thoughts influencing distant objects. Its strangeness is not a license to say anything. The narrower claim is already enough. The complete physical description of a composite quantum system cannot always be built from independent descriptions of its parts. A pair of entangled particles is like two marks in a ledger that cannot be understood by reading either entry alone. The relation is not a third object sitting between them. It is part of the accounting rule that links what can be found on each side. The metaphor is limited, but it keeps the mechanism in view. The power lies in correlation, not in a hidden beam crossing the distance. Entanglement also helps clarify why measurement is such a large problem. When a small quantum system interacts with a detector, it becomes entangled with the detector. One possible system result becomes correlated with one detector state. Another possible result becomes correlated with another detector state. If the detector is then entangled with the environment, the possible records become amplified and stabilized. The small system's alternatives are no longer isolated. They have spread into the apparatus and surroundings. This is how a microscopic possibility becomes a macroscopic trace. A photon hits a detector material, an electron may be released, a current may be amplified, a pixel may change state. That change may be stored in the electronics, displayed on a screen, written to memory, and later seen by a person. At each step, correlations multiply. The original quantum event becomes a durable record because it is copied into many degrees of freedom. The fragile amplitude relation that once allowed interference is no longer locally recoverable. There is a physical violence in amplification, though it is quiet. A microscopic event becomes too large to unmake. Not impossible in a logical sense if one imagined total control over the full quantum state of everything involved, but impossible for any realistic apparatus. The record spreads. The environment becomes contaminated with information about the outcome. Reversing it would require gathering every scattered trace and restoring the exact phase relations. The universe does not need to forbid that with a new law for ordinary measurement to become effectively irreversible. The word irreversible must also be handled carefully. At the level of fundamental equations, many quantum processes are reversible in principle. At the level of macroscopic records, reversal becomes practically unattainable, because information has dispersed into too many places. This is close in spirit to thermodynamics. A perfume molecule can spread through a room. The equations of motion may not forbid the molecules from returning to the bottle. But the practical probability is so small that irreversibility becomes the condition of experience. A detector record has a similar directionality. Once the result has been amplified into many degrees of freedom, it becomes part of the classical-looking history of the laboratory. The screen displays one mark. The memory chip stores one value. The notebook contains one number. The result can be shared because it is stable. Science depends on that stability. Without it, experiments would not leave facts behind. And yet this stability has emerged from a quantum process whose mathematical description began with alternatives. The detector is classical enough to record one value, but quantum enough in its parts to become entangled and decohere. That double role is the heart of the measurement problem in modern form. Measurement is neither a mere glance nor a simple collision. It is the physical production of a stable, communicable record from a system described by quantum possibilities. The old image of collapse becomes less like a sudden magical cut, and more like a narrowing of access. Before measurement, the amplitudes can interfere because the alternatives remain coherent. During measurement, the system becomes correlated with the apparatus. Through decoherence, those correlations spread into the environment. Afterward, the local world presents one stable record. Whether one says the wave function truly collapsed, or that branching occurred, or that the wave function was only a state of knowledge updated by the record depends on interpretation. The physical mechanism of correlation and decoherence is not optional. This layered picture gives quantum physics much of its modern power. It explains why microscopic systems can show interference, while macroscopic instruments show definite readings. It explains why protecting coherence is so hard and so valuable in quantum technologies. Quantum computers, for example, depend on maintaining delicate superpositions and entanglement long enough to perform controlled operations. Decoherence is one of their great enemies because environmental leakage turns quantum advantage into ordinary noise. The same mechanism that makes the everyday world stable makes quantum control difficult. A qubit must be isolated enough to preserve coherence, yet connected enough to be prepared, manipulated, and measured. Too much isolation makes it unusable. Too much contact destroys the fragile phase information. The engineering problem mirrors the philosophical one in physical form. Quantum possibilities must be protected until the moment they are deliberately converted into records. This gives the measurement problem a practical edge. It is not only a question for interpretation, it shapes real devices. It determines how experiments are shielded, cooled, timed, and read out. It decides whether entanglement survives long enough to be useful. It decides whether interference can appear or fade. The philosophical discomfort is attached to laboratory hardware. The deeper pattern now becomes visible. The double-slit showed that distinguishability destroys interference. The wave function showed that possibilities carry amplitude structure, not ordinary ignorance. Collapse named the transition from possible outcomes to one record. Decoherence explained how environmental information erases accessible interference and stabilizes classical-looking facts. Entanglement showed that quantum systems can possess joint states that are not reducible to independent parts. These are not separate curiosities. They are different faces of the same pressure on classical intuition. At every step, the old picture asks for ready-made properties. The photon should have one path. The detector should reveal what was already there. The apparatus should be separate from the system. The two particles should carry their own answers. The large world should be simply definite. Quantum physics replies with conditions. Which paths are distinguishable? Which amplitudes remain coherent? Which information has leaked into the environment? Which measurement is performed? Which correlations can be compared? This does not make reality arbitrary. The conditions are physical, not psychological. Change the apparatus, and the statistics change in calculable ways. Preserve coherence, and interference can appear. Record which path, and interference is lost. Entangle particles and correlations violate classical bounds. Expose a system to an environment, and classical behavior emerges. The rules are strict. What they deny is not law. They deny a certain kind of hidden classical account. That denial is difficult because human imagination evolved inside the stable world produced by decoherence. We picture objects moving along paths because the objects we handle behave that way. We picture measurement as looking because most measurements around us reveal stable properties that are already redundantly recorded by the environment. We picture separated things as independent because tables, stones, tools, and planets can often be treated that way with extraordinary success. Quantum experiments are difficult not because they are vague, but because they isolate nature from the very interactions that trained our intuition. A single photon in a protected apparatus is not part of the ordinary traffic of traces. It is more like a message sealed from the environment until the instant it reaches the detector. If no path record is made, the message retains the phase relation between alternatives. If a record is made, the alternatives separate into distinguishable histories. If the message becomes entangled with uncontrolled surroundings, the coherence is lost from the part we can observe. The experiment is a way of deciding which traces the world is allowed to keep. There is a quiet severity in that sentence. The world we call classical is full of kept traces. The quantum world appears when traces are withheld. Measurement is the creation of a trace strong enough to enter the shared record. The cost of the trace is the loss of interference between alternatives that the trace distinguishes. That cost appears on a screen as bands disappearing. It appears in technology as decoherence. It appears in foundations as the measurement problem. Now, the detector at the end of an experiment looks less like a passive endpoint. It is a place where possibility becomes history. The photon does not arrive as a little classical account with all details attached. It arrives as a quantum system whose possible outcomes have been shaped by amplitudes, coherence, apparatus, and environment. The detector does not ask every possible question. It asks one physically defined question, and the world answers with one event. The answer, however, is not chosen by the equations in the old deterministic way. Quantum theory gives the probability for each outcome. It gives the statistical pattern over many repetitions. It gives the interference structure, the correlation rules, the effect of decoherence, and the conditions under which records form. But when a single detector fires in one place rather than another, the theory does not usually say, with classical necessity, that this individual result had to occur. That leaves the next pressure point exposed. The world is not lawless. The probabilities are precise. It is not merely ignorant. Bell-type experiments undermine the simplest local hidden instruction stories. It is not created by human looking. Detectors and environments make records without us. It is not simply classical underneath. Interference and entanglement forbid that easy return. And still, in one run of the experiment, one value appears. If quantum theory can predict the pattern of many events with such precision, why does a single event arrive as a genuine outcome that no calculation seems able to force in advance? In the classical world, randomness usually means that something is hidden from us. The coin is already spinning with a precise speed and angle. The air around it already has a precise pattern of motion. The table is already weighting with a precise texture, hardness, and tilt. We call the result uncertain because we do not know all the details. The coin itself in the classical picture is not undecided. The same kind of uncertainty appears everywhere in ordinary life. A raindrop slides down a window and turns left instead of right because of invisible ridges, dust, surface tension, and microscopic variations in the glass. A leaf twists through air because small currents push it differently from moment to moment. A stone thrown into a stream bounces in a way that is hard to predict because too many forces act at once. But the hidden assumption remains steady. If every detail were known, the path would be fixed. Quantum mechanics removes that easy shelter. Even when the wave function is known as completely as the theory allows, it generally does not give one guaranteed result for a single measurement. It gives probabilities. It tells us the distribution we should expect after many repeated trials. It can predict the shape of the double-slit pattern, the rates of atomic transitions, the correlations between entangled particles, and the statistics of spin measurements. But in a single event, the detector may still fire in one allowed way rather than another, with no deeper classical cause supplied by the standard theory. This is not disorder in the loose sense. It is not a failure of mathematics. The probabilities are precise enough to build modern electronics, lasers, imaging devices, atomic clocks, and quantum experiments of extraordinary sensitivity. The strange part is that the law becomes statistical at the point where classical intuition expects it to become most exact. The theory is not weak because it gives probabilities. It is powerful because it gives the right probabilities. But it does not usually tell us which one permitted result must happen next. A fair coin in the air and a photon at a detector therefore belong to two different kinds of uncertainty. The coin's uncertainty is epistemic. It comes from incomplete knowledge. The photon's uncertainty, in many standard readings of quantum mechanics, is deeper. It is not merely that a pre-written answer is hidden in a place we cannot reach. Certain measurement results are not treated as having definite classical values before the measurement context makes them actual. That distinction sounds abstract until it is placed back in the laboratory. Prepare identical photons, send them one at a time toward the same two slits, keep the apparatus unchanged, and record the impacts. The pattern after many photons will be stable, but any one photon does not come with a predictable landing point. The wave function gives a landscape of probabilities. The detector gives a point. Between them lies a kind of selection that the usual equations constrain but do not turn into a classical mechanism. Einstein resisted this claim because he saw what it would cost. His objection was not that quantum mechanics failed in practice. It worked too well to ignore. The problem was whether its success meant that nature itself was irreducibly probabilistic, or whether the theory was incomplete. Perhaps beneath the wave function, there were hidden variables, additional facts not yet included in the theory, facts that would restore definite causes to individual outcomes. That hope was not foolish. Physics had often explained apparent randomness by finding a deeper mechanism. Heat became molecular motion. Pressure became countless impacts of particles against walls. Chemical spectra became transitions between quantized energy levels. What looked like irregularity often became law once the hidden layer was found. It was natural to ask whether quantum randomness was another case of ignorance waiting for a better theory. But quantum mechanics does not allow the simplest version of that escape. The decisive pressure came from entanglement and Bell's theorem. If particles carried complete local instruction sets before measurement, and if no physical influence travelled faster than light, then the correlations between distant measurement results would have to obey certain mathematical limits. Those limits are Bell inequalities. Experiments have repeatedly found correlations that violate them in the way quantum mechanics predicts. The consequence is narrow, but severe. It does not prove that every possible hidden variable idea is impossible. It does not prove that faster-than-light messages can be sent. It does not turn randomness into mystical freedom. It does remove the comfortable picture in which each particle simply carries all its answers locally, like sealed instructions in a box, waiting for measurement to reveal them. The quantum correlations are too strong for that simple world. This leaves several paths, none of them classical. One can accept genuine quantum indeterminacy. One can adopt a theory with hidden variables, but then the hidden structure must be non-local in a precise way. One can deny that only one outcome exists in the old sense, as many worlds' interpretations do. One can treat the wave function as information rather than a physical object. Different interpretations take different costs. What the experiments remove is the idea that nothing deep has happened and that ordinary hidden ignorance will be enough. A detector click therefore has a peculiar status. It is not lawless, because its probabilities are governed by the quantum state. It is not simply predetermined in the classical local way, because Bell-type correlations block that route. It is not created by human awareness, because detectors record outcomes without being watched. It is an event constrained by a mathematical structure that does not behave like a list of hidden classical facts. The world becomes more exact and less picturable at the same time. This is the place where quantum randomness begins to feel less like noise and more like architecture. In a random number table, no single digit may be predictable, but the rules of the table may still be carefully tested. In quantum mechanics, the individual result appears without a classical guarantee, yet the whole distribution is rigidly structured. The dark bands in interference do not fill randomly. The spin correlations do not drift arbitrarily. The atom does not emit any energy it likes. The randomness is bounded by the wave function, by symmetry, by conservation laws, by the apparatus, and by the question the measurement physically asks. That is why the phrase "anything can happen" is wrong. Quantum physics is not a permission slip for impossibility. It is a theory of sharply limited possibilities. The possible outcomes are determined by the state and the measurement. The probabilities are calculated by rules. What is not supplied in the usual formulation is a classical account selecting the one outcome in advance. The range is lawful. The individual event remains probabilistic. Imagine a narrow harbour entrance at night, with buoys marking channels that no boat can ignore. The sea may decide the exact timing of each wave hitting the stones, but not every pattern is allowed. Some motions are impossible because of the shape of the harbour. Others are favoured because of wind and tide. The image is imperfect because quantum amplitudes are not water, yet the constraint matters. Quantum randomness is not emptiness, it is uncertainty inside a structure. The difficulty grows when time is brought back into the picture. In the ordinary world, a measurement seems to come after the event it measures. A car first passes a point, then the camera records it. A bird first flies over a roof, then a person sees it. A raindrop first lands, then a mark appears on the glass. The past is assumed to have a finished classical form, even if we learn about it later. Quantum experiments make that instinct less secure. They do not show that the future sends usable messages into the past. They do not give a machine for rewriting history. But they do show that some questions about what a system was doing between preparation and measurement cannot be separated from the final experimental arrangement. The past of a quantum system is not always a clean classical path waiting behind the measurement. John Wheeler sharpened this unease with delayed choice experiments. In their simplest spirit, the question is whether the decision to reveal wave-like interference or particle-like path information can be made after the quantum object has already entered the apparatus. A photon travels through an interferometer. Classical imagination wants to say that by the time it reaches the later part of the setup, it must already have behaved either like a wave taking both routes or like a particle taking one. Wheeler's idea presses on that sentence. An interferometer can split and recombine paths. If the paths are recombined so that no which path information exists, the amplitudes can interfere and the result bears a wave-like signature. If the setup allows the paths to remain distinguishable, the result carries particle-like path information. In delayed choice versions, the decision about whether to recombine or distinguish the paths can be made after the photon has passed the point, where classical intuition wanted the route to be fixed. The tempting phrase is that the later choice decides what the photon did in the past. That phrase should be handled with care. It is too dramatic, and it suggests a backward signal that the experiments do not require. A safer statement is already strong enough. The photon cannot be assigned a complete classical history independent of the measurement context. The final arrangement determines which kind of phenomenon can be recorded. And the language of a pre-existing wave or particle behavior becomes unstable. The mechanism is not psychological. Nothing depends on a human making a dramatic last-second decision with conscious attention. A fast device can change the configuration. The apparatus can be arranged so that one kind of information is available or not. What matters is whether the paths remain coherent and indistinguishable, or whether the experiment contains the physical means to tell them apart. The later setting defines what correlations and interference effects can appear in the final records. The hallway image is tempting here. A photon enters a corridor with two possible routes. At the far end, a set of doors determines whether the routes are recombined or kept separate. If the doors recombine the paths, the final record cannot honestly be described as a particle that simply took one corridor like a dust grain. If the doors preserve path information, the interference vanishes. The last door does not send an instruction backward down the hallway. It determines what kind of complete experimental history can be meaningfully assigned. This is the sharpest lesson of delayed choice. The experiment does not reveal a hidden decision made by the photon at the beginning. It reveals that the classical demand for such a decision may be the wrong demand. The quantum state evolves through the apparatus according to the full physical setup. Only when the measurement context is complete do certain questions gain definite answers. A route is not merely unknown. In some arrangements, the route is not a classical fact the experiment supports. That is difficult to accept because ordinary time is built out of records. A footprint means something pressed the ground earlier. A scratch on metal means contact happened. A message on a screen means a signal was processed. In macroscopic life, records allow us to reconstruct past events with confidence. The world has so many traces that the past feels like a fixed archive. Quantum experiments strip away most of those traces. They ask what can be said when the record is not yet made, or when the record is arranged to preserve coherence rather than reveal a path. If the only possible records at the end are wave-like interference results, then forcing a particle path into the earlier event adds a classical picture that the experiment does not justify. The past has not become unreal. The problem is that the kind of past we are allowed to infer depends on the kind of record the experiment creates. Delayed choice experiments therefore do not make time meaningless. They make classical storytelling insufficient. The sequence of laboratory events remains ordinary: preparation, propagation, setting, detection, record. The equations respect the experimental order. No message travels back for practical use. But the narrative we attach to the photon cannot be a little movie of a definite object, carrying definite values through every unmeasured step. The movie is an image our scale taught us to expect, not a requirement imposed by the experiment. A related set of experiments, often called quantum eraser experiments, presses on the same weakness from another side. The basic idea is to mark which path information and then arrange conditions under which that information is erased or made unavailable for selected comparisons. When path information is available, interference disappears in the directly observed distribution. When the data are sorted according to certain correlated measurements, interference-like patterns can reappear in subsets. These experiments are often described in misleading ways. They do not show that a later human decision changes an earlier event in a simple causal sense. They do not allow messages into the past. They do not mean that forgetting something in a person's mind restores a wave. The erasure is physical and statistical. It concerns whether information distinguishing alternatives remains available in the correlations used to analyze the results. If the alternatives cannot be distinguished within that chosen correlation structure, interference can be recovered in the sorted data. The careful point is again about information, not memory in the ordinary human sense. A which path mark correlates a photon's alternative paths with another physical system. That correlation destroys the interference in the unsorted pattern. If a later measurement is made in a way that no longer reveals which path, the joint data can show interference within appropriate subgroups, but the total record still contains no usable retrocausal signal. Only after comparing records through ordinary communication does the interference structure emerge. A laboratory screen in such an experiment may look unimpressive at first. Just a broad distribution of detection events, no clear bands. The bands appear only when the records are separated according to the outcomes of another measurement. The hidden order is not visible in one stream alone. It is in the correlations. That matters because it prevents a false magical reading while preserving the real discomfort. Whether interference appears can depend on how physical information about alternatives is encoded and compared. The pattern is now familiar. When alternatives remain coherent and indistinguishable, amplitudes can interfere. When information distinguishes them, interference is lost. When the information is erased in the relevant measurement basis, interference can be recovered in correlated subsets. The principle does not require a mind-rewriting nature. It requires quantum states, correlations, measurement bases, and the physical availability of information. This is a more disciplined kind of strangeness. It gives up the easy drama of the observer creates reality, but it keeps the harder fact. The quantum world does not separate cleanly into what happened and how we later decide to ask about it. The question, the apparatus, the measurement basis, and the record are part of the phenomenon, not because they are subjective whims, but because they define which physical alternatives can interfere and which cannot. The measurement basis is the set of possible answers a measurement is built to distinguish. A polarizing filter asks one kind of question about light. A detector at a slit asks a path question. A screen behind two slits asks a position question. A spin apparatus oriented one way asks for spin along the axis. Rotate it, and the question changes. Quantum systems do not necessarily carry definite answers to all possible questions at once. The act of choosing a measurement basis is the act of choosing which set of possible outcomes can become records. That statement does not mean the experimenter controls the answer. It means the experimenter controls the question. The result within that question remains probabilistic, except in special cases where the state guarantees an outcome. A polarizer may define what counts as transmitted or blocked. It does not allow the experimenter to command a single photon to be transmitted at will. The structure is controlled, the individual result is not. This distinction is essential. Without it, quantum theory slides into exaggeration. Measurement is not arbitrary creation. It is constrained selection under a defined physical arrangement. The apparatus defines the possible records. The quantum state gives the probabilities. The detector produces one event. The experimenter can choose the arrangement, but cannot usually choose the outcome. The power of measurement is real, but bounded. The old mechanical universe is no longer merely damaged at one edge. Its central habits have been replaced. A particle does not always carry a definite path. A property does not always have a pre-existing classical value. Randomness is not always ignorance. A measurement is not merely a glance. A past quantum history is not always a classical path waiting to be uncovered. Separate parts of a system may not have independent states. The world has not become vague. It has become more conditional than the old picture allowed. The natural question is whether this conditional structure is the final word or only the surface of a deeper theory. Interpretations of quantum mechanics are attempts to answer that question without changing, in most cases, the experimental predictions that have already been tested. They do not usually disagree about the double-slit pattern, the Bell correlations, or the practical rules for calculating measurement outcomes. They disagree about what the mathematics says the world is doing when those rules work. The Copenhagen family of views keeps the emphasis on experiments, conditions, and recorded outcomes. It avoids asking for a classical picture of what the system did between preparation and measurement, when no such picture is experimentally defined. In this spirit, quantum mechanics is a framework for predicting the results of measurements under specified arrangements. It is cautious about claims beyond that. The cost is that it can feel incomplete to anyone who wants a continuous picture of microscopic reality. Many physicists have found that caution useful. It blocks the temptation to smuggle classical images back into a theory that has already outgrown them. It insists that words like path, position, and spin receive their meaning through experimental arrangements. It keeps the laboratory record at the centre of the science, but it does not satisfy the deeper hunger for a clear account of what exists when no measurement is being made. For that reason, other interpretations take bolder routes. The many worlds interpretation removes collapse. In this view, the wave function always evolves smoothly according to the quantum equations. When a measurement occurs, the observer, apparatus, and system become entangled. Instead of one outcome being selected by a special collapse process, the different outcomes correspond to different branches of the universal wave function. Each branch contains a version of the observer seeing a definite result. This interpretation is often sensationalized, so the careful version matters. It does not say that every fantasy becomes real. It does not say that human choices magically spawn worlds in a mythic sense. It says that the mathematical wave function is taken seriously as a complete physical description, and that what we call a measurement is branching through entanglement and decoherence. Each outcome appears definite within its branch, because branches no longer interfere in any accessible way. The strength of this view is its mathematical cleanliness. It avoids adding a special collapse rule. The same quantum evolution applies to photons, detectors, laboratories, and observers. Decoherence explains why branches become effectively separate. The cost is ontological weight. One must accept a vast structure of branching outcomes, even though each observer experiences only one. The single detector click is explained not by the destruction of other possibilities, but by the observer finding themselves in one branch of a larger quantum state. For some, that is elegant. For others, it is too much to believe. The disagreement is not about whether the double-slit pattern appears. It is about what the unused amplitudes are. Did they collapse away? Were they only part of a calculation? Or do they persist as parts of a larger wave function, with each branch carrying its own internally consistent record? The same laboratory result becomes the entrance to different pictures of reality. Pilot wave theory, associated with Louis de Broglie and later David Bohm, takes another route. It restores particles with definite positions, but guides them with a real wave. In this view, a photon or electron has an actual configuration, while the wave function evolves and directs the motion through a guiding equation. The particle goes through one path, but the pilot wave can pass through both slits and shape where the particle lands. This gives back something classical intuition wants: definite trajectories. In a double-slit experiment, the particle has a path. The interference pattern arises because the guiding wave contains information about the full arrangement, including both slits. The particle's final distribution matches quantum predictions because its motion is guided by the wave function. The cost is non-locality. To reproduce entanglement correlations, the guiding structure cannot remain local in the simple classical sense. The state of the whole system matters at once in a way that does not allow faster-than-light signaling, but does violate the old independence of distant parts. Pilot wave theory shows that quantum randomness need not be interpreted in only one way. The apparent randomness can arise from ignorance about initial conditions within a deterministic, hidden variable theory. But the price is not a return to Newton's quiet machine. The hidden variables must live inside a non-local quantum structure. The old dream returns changed. Determinism can be saved only by giving up locality in the simple form Einstein wanted. Objective collapse theories choose a different cost. They propose that collapse is a real physical process, not merely an update of knowledge and not merely branching. In these theories, the wave function sometimes collapses spontaneously, or under conditions related to size, mass, or complexity. Microscopic systems can remain in superposition for a long time, but macroscopic superpositions are unstable because collapse becomes more likely as systems grow. The appeal is clear. These theories try to explain why we see one outcome without relying only on observers or interpretation. They modify the dynamics so that the transition from possibility to fact is built into physical law. The cost is that the modification must be tested and constrained. If collapse happens too often or too strongly, it would conflict with known quantum interference. If it happens too rarely, it may not solve the measurement problem. Experiments continue to place limits on such models, and no objective collapse theory has become the settled replacement for standard quantum mechanics. There are also interpretations that treat the wave function more as information than as a physical wave. In these views, collapse can resemble an update in expectations after a result is obtained. The wave function does not have to be a material object spread through space. It can be a tool used by an agent or observer to assign probabilities to future experiences or records. Such views can make the collapse less physically violent, but they face their own burden. Explaining why different observers can agree on stable experimental facts, and how the shared world remains so reliably structured. Relational approaches shift the emphasis again. A property may be definite, relative to one system that has interacted with another, but not absolute in the detached classical sense. The result of a measurement is a fact for the systems involved in the interaction, while a more distant system may describe the combined pair differently until it interacts with them. This view tries to take seriously the idea that physical properties arise in interactions, not as isolated labels carried independently by objects. Each interpretation handles the same pressure differently. Copenhagen limits what can be said outside measurement contexts. Many worlds keeps the wave function and removes collapse. Pilot wave theory restores trajectories but accepts non-local guidance. Objective collapse makes collapse a real physical process. Information-based and relational views rethink what the wave function and properties represent. None has forced universal agreement. The experiments are clear, the meaning remains contested. This is not a weakness in the usual sense. It is a sign that quantum mechanics gives predictions more easily than pictures. The mathematics tells the detector what distribution to produce. The laboratory confirms the pattern. But when the mind asks for an account with objects, paths, causes, and a single outcome, the theory offers several ways to translate the mathematics, each with a price. The price cannot be avoided by saying, "Shut up and calculate," although that attitude has often been useful in practice. Calculation built technologies and tested predictions. But the measurement problem remains because the world contains actual records, not just probability tables. A detector does not merely calculate its own possible clicks, it clicks. A laboratory notebook contains one number. A later scientist reads one result. The existence of definite records is precisely what any interpretation has to account for. A single event is where all the large arguments become small again. A photon hits the detector, the pixel changes, the rest of the screen does not. If one repeats the experiment, the statistics follow quantum law. If one asks why this pixel fired in this run, the answer depends on how one interprets the theory. The event is tiny, but it carries the weight of the whole dispute. Probability, measurement, information, non-local correlation, decoherence, and the status of the wave function. This is why quantum mechanics feels less like one mystery than a pressure system pushing against many classical assumptions at once. The double-slit questions path. Bell tests question local hidden properties. Delayed choice questions classical histories. Decoherence questions the boundary between quantum and classical. Interpretations question whether collapse is real, apparent, informational, or unnecessary. The same mathematics stands behind all of it. But our ordinary images break in different places. The safe claim is not that reality is unreal. That phrase is too blunt to be useful. The safer claim is sharper. Reality at the quantum scale is not organized according to the classical categories our senses were trained to trust. Path, property, cause, and record still exist, but they have to be tied to experimental conditions. A photon is not a pebble too small to see. A measurement is not a glance made more precise. A probability is not always ignorance. A correlation is not always a pair of hidden instructions. In the quiet of the laboratory, the apparatus does not care which interpretation a physicist prefers. It responds to the arrangement. If the paths are coherent, interference appears. If which path information exists, the pattern changes. If entangled particles are measured, the correlations exceed classical local bounds. If the environment takes the phase information away, the world becomes effectively classical. The detector does not settle the metaphysics. It enforces the constraints. That may be the most unsettling form of scientific mystery, not a lack of knowledge, but a surplus of correct prediction without a single agreed image beneath it. The equations are strong, the experiments are repeatable, the technologies work, yet the account of what happens between preparation and record remains open enough that careful physicists can disagree without disagreeing about the data. At the end of this stage, the photon has not become easier to picture. It has become harder to mispicture. It is not a little glowing grain choosing one slit in secret. It is not a mist of human imagination. It is a quantum system whose possible records are shaped by amplitudes, measurement basis, coherence, entanglement, and environment. When the record forms, one result enters the world we can share. The question that remains is whether that single result is the only thing that happened, the only thing we can access, or only one visible face of a deeper quantum structure. The diversity of interpretations can feel unsettling, because physics is often imagined as the discipline that tells us what the world is. A measurement is made, a number is written down, and the argument ends. But quantum mechanics separates two layers that ordinary thinking tends to fuse together. One layer is experimental and computational. In that layer, the theory is remarkably firm. It tells us how to prepare systems, how to calculate probabilities, how interference appears, how entanglement is tested, and how devices can be built from quantum rules. The other layer is ontological. What kind of picture of existence corresponds to those calculations? That second layer is where the disagreement lives. Different interpretations often give the same predictions for the experiments we can perform. They do not usually disagree about the bright and dark bands in the double-slit experiment, the disappearance of interference when path information exists, or the statistical correlations measured in entangled systems. They disagree about what those facts mean. Was there a collapse? Was there branching? Was the wave function a physical object? A tool of prediction, or something relational between systems, the detector gives the same point either way. This is why the uncertainty around interpretation is not the same as confusion about the physics. It is not a fog in which nothing is known. It is a sharply bounded gap. We know how to calculate the patterns. We know which classical intuitions fail. We know that ordinary hidden path stories do not reproduce the results. We know that measurement is physical, not psychological. What remains open is the deeper image beneath the working mathematics, what the quantum state is. and how one stable record becomes the fact that a laboratory can share. That distinction gives quantum theory its unusual emotional pressure. It is not weak enough to ignore, and not picturable enough to settle into common sense. It works so well that the world must obey it. Yet it works in a way that resists the old habits of thought. It predicts the behavior of atoms, semiconductors, lasers, magnets, detectors, molecular bonds, and the fragile systems being engineered for quantum computers. It is one of the most successful scientific frameworks ever built. But the little account we want to tell about the photon between source and screen remains incomplete. John Wheeler was one of the physicists willing to push this incompleteness into a broader frame. His phrase, participatory universe, is easily misunderstood, especially when pulled away from the discipline of experiment. It does not mean that human thoughts rewrite the laws of nature. It does not mean that desire or attention can command particles to behave as we wish. The stronger claims are not supported by quantum mechanics. Wheeler's question was more restrained and more difficult. What if the acquisition of information is not a passive decoration added to reality, but one of the ways physical reality becomes describable as a set of definite facts? The double-slit experiment contains this question in miniature. When no path information exists, interference can appear. When the path becomes distinguishable, the interference disappears. In delayed choice experiments, the meaning of wave-like or particle-like behavior cannot be cleanly separated from the complete measurement arrangement. In entanglement, individual outcomes remain random, while correlations reveal a joint quantum state. In each case, information is not a thought floating outside matter. It is a physical relation, a record, an interaction, a correlation between system and apparatus. Wheeler's it from bit can be treated as a philosophical proposal, not as a completed theory of everything. It suggests that physical facts and informational distinctions may be more deeply linked than classical physics assumed, but it should not be inflated into the claim that the universe is literally made of human knowledge, or that consciousness creates particles by looking at them. The safer and stronger point is that physics cannot describe a measurement without specifying what information is made available, what alternatives are distinguished, and what kind of record enters the world. The word participate becomes less mystical when it is brought back to the laboratory. A physicist participates by building an apparatus, choosing a measurement basis, controlling the environment, and reading a record. The apparatus participates by interacting with the system. The environment participates by carrying away phase information. The detector participates by turning a microscopic event into a stable trace. No part of this chain stands outside nature. The observer is not a ghost over the experiment. The observer is another physical system, late in a chain of interactions that began with matter meeting matter. This reframes objectivity. Objectivity does not require that every property already exist in a classical form before any possible measurement. It requires shared procedures, reproducible statistics, stable records, and constraints that do not depend on private feeling. A detector click can be checked. A pattern can be repeated. A Bell test can be performed with controlled settings. A quantum device can be engineered by people who do not share a philosophy of the wave function. The objectivity lies in the repeatable structure of the results, not in the old belief that all classical answers were silently written into the system from the beginning. The universe, in this careful sense, does not look like a finished stage with an audience sitting outside it. It looks more like a network of physical relations in which some events become definite for other events by leaving traces. A photon changes a detector. The detector changes an electronic circuit. The circuit changes a memory state. The memory state changes a screen or a file. A human later reads the record and places it into a larger web of comparison, calculation, and communication. At each step, possibility is converted into a more stable form of information. That chain is ordinary and strange at once. Ordinary because every laboratory depends on records. Strange because quantum mechanics shows that the availability of a record can decide whether interference survives. The record is not merely a note after the event. It is part of the physical conditions that separate alternatives from one another. When the world can tell which path was taken, the alternatives cannot continue to combine in the same way. A fact has a cost. This is the clean meaning of the observer effect. It does not mean that human consciousness freely creates reality. It means that in quantum physics, measurement is not a passive glance. It is a physical process that determines what kind of information is available and which quantum alternatives remain capable of interfering. When the word observation appears, it is safer to hear detection, interaction, record, distinguishability. A person may be the final reader, but the physical chain begins before anyone looks. The misconception persists because the everyday word observer is too human. It carries eyes, attention, curiosity, intention. In the laboratory, the essential observer may be a cold detector, a crystal lattice, a trapped ion, a photographic plate, or the surrounding environment. It may have no memory except to change physical state. It may have no awareness at all. What matters is whether the system's alternatives become correlated with something else in a way that can, in principle, distinguish them. This is why a sealed experiment does not wait for a human to open the door. If a detector has registered which slit a photon passed through, the interference is gone whether the data are read immediately, read tomorrow, or never read by a person at all. The path information has been physically encoded. The fact that no one has yet looked at the display does not restore the lost coherence. The damage, if we can call it that, was done by the existence of a distinguishing record. And yet even the word damage is imperfect. The loss of interference is not a malfunction. It is the natural cost of turning a quantum alternative into a classical trace. Without that cost, no experiment would give stable facts. A detector that did not create records would not measure. A world in which no information was ever amplified into durable form would not contain the kind of shared reality science can use. The same process that hides quantum interference makes observation possible. Decoherence explains why this process becomes so fast and irreversible in practice at ordinary scales. Once information leaks into the environment, delicate phase relationships disperse. Large objects become classical looking, not because they stop being made of quantum matter, but because they are too open, too warm, too entangled with their surroundings. A cabinet, a tree, a human body, a grain of dust in sunlight. Each is continuously exchanging photons, air molecules, thermal radiation, vibrations and forces with the rest of the world. A grain of dust is small by human standards, but enormous as a quantum system. Light scatters from it in many directions. Air molecules collide with it. Heat flows through and away from it. Every one of those contacts can carry away a small amount of information about where the grain is. For the grain to show visible interference between two different positions, all those environmental traces would have to remain controlled or erased. In an ordinary room, that never happens. The room is already measuring the grain. The word measuring here should still be heard physically. The room has no intention. It has no inner witness. It is simply filled with interactions that create correlations. A photon that bounces off the grain carries information. A molecule that strikes it carries information. A thermal emission carries information. The environment becomes a vast, uncontrolled archive of traces. By the time a human sees the dust in a beam of light, the dust's position has already been redundantly recorded by the world around it. This is the mechanism behind the emergence of the classical world. Emergence means that a new kind of behavior appears from many underlying parts, without being present in the same way in each part alone. Temperature is not a property of one isolated molecule in the ordinary thermodynamic sense. It describes the statistical behavior of many particles. Solidity is not a tiny block of hardness inside each atom. It emerges from electromagnetic forces, quantum rules, and the collective structure of matter. Classical definiteness emerges similarly as a stable approximation when quantum systems are large, open, and constantly entangled with their environments. That does not make classical physics false, it makes it scale-dependent. We do not need the wave function of a mug to place it on a shelf. Engineers do not calculate every quantum amplitude when designing a bridge. Astronomers can track planets with equations that existed long before quantum theory. because planets are large objects whose relevant behaviour is extremely well described by classical and relativistic mechanics. A good approximation is not an illusion. It is a language that works under the right conditions. The failure appears only where the approximation is pushed beyond its territory. A single photon, a trapped ion, a superconducting circuit cooled and isolated from its environment, an electron spin, an atom passing through an interferometer. These systems can preserve quantum coherence long enough for non-classical behaviour to matter. There, the classical language of ready-made paths and passive measurement begins to break. The boundary is not drawn by human wonder. It is drawn by isolation. Interactions, scale, temperature, and the survival of phase relationships. This is why quantum experiments have to be engineered with such care. They are not revealing a separate magical realm. They are protecting ordinary matter from ordinary contact long enough for its quantum structure to remain visible. Vacuum chambers, cryogenic temperatures, shielding, timing, and precision control are not decorations around the experiment. They are the conditions that stop the environment from stealing the information too early. To show interference, one must prevent the world from learning the path. The same fragility makes quantum technologies difficult. A qubit must maintain superposition and sometimes entanglement long enough to be useful. It must be isolated from unwanted noise, but still accessible to control pulses and final measurement. Too much contact with the environment destroys coherence. Too little contact makes the system impossible to prepare and read. The engineering problem is a physical version of the measurement problem. How to preserve possibility until the moment when possibility must become a record. Quantum cryptography, quantum sensors, and quantum computing all use this tension. They do not work because quantum physics is vague. They work because the rules are strict. A quantum state cannot always be copied freely. Measurement can disturb a system. Entanglement can create correlations stronger than classical shared instructions. Superpositions can be transformed by controlled operations before decoherence destroys them. The technology depends on treating quantum fragility not as a nuisance alone, but as a resource. Entanglement gives another form of humility. It shows that parts of the world can share a state whose correlations cannot be explained by a simple stock of local properties. But it also sets boundaries against fantasy. Entanglement does not allow chosen messages to travel faster than light. It does not let a person control a distant event by deciding what they want. Individual outcomes remain random. The correlations become visible only after records from both sides are compared through ordinary communication. Quantum strangeness is precise enough to be tested and strict enough to forbid many of the stories people attach to it. This matters because quantum physics is often borrowed as a language for claims it does not support. The word observer becomes consciousness. The word possibility becomes wish. The word entanglement becomes mystical connection. The word energy becomes a vague substance that explains whatever one wants it to explain. Each step weakens the real science. The actual theory is more demanding and more interesting. It does not say anything can happen. It says exactly which probabilities can happen under exactly which physical conditions. The same discipline is needed when quantum ideas enter biology. Living organisms are warm, wet, noisy, chemically active systems. Cells are full of collisions, vibrations, thermal motion, molecular fluctuations, and environmental disturbance. At first glance, that seems like the worst possible setting for delicate quantum coherence. And in many cases, it is. Large biological structures do not sit in long-lived macroscopic superpositions. A leaf, a bird, or a brain is not a mystical quantum object in the sensational sense. But life operates at molecular scales, and molecules are quantum systems. Chemical bonds are quantum. Electron orbitals are quantum. Absorption and emission of light are quantum. Proton and electron transfer can involve quantum behavior. The cautious question in quantum biology is not whether biology is secretly exempt from quantum mechanics. It is whether some organisms exploit specific quantum effects in functional ways before noise destroys them. Photosynthesis is one of the most studied examples. When a photon strikes a pigment molecule in a leaf or photosynthetic bacterium, its energy can become an excitation that moves through a molecular complex before helping drive chemical reactions. Some experiments have indicated that, in the earlier stages of energy transfer, short-lived quantum coherence may play a role. The careful version of the claim is narrow. It does not mean the whole leaf is in a mystical superposition. It means that an excitation inside a molecular complex may retain wave-like relationships briefly enough to influence how energy explores transfer pathways. That possibility is scientifically interesting precisely because the environment is noisy. The biological structure may not need to isolate quantum coherence perfectly. It may only need to use it quickly, or tune the molecular environment so that noise and coherence work together rather than simply fighting. A pigment complex is not a temple of mystery. It is a physical structure with distances, couplings, vibrations, and timescales. If coherence helps energy transfer, it does so through molecular dynamics, not through vague life force. Bird navigation offers another careful example. Some birds can orient using Earth's magnetic field, which is extremely weak compared with many everyday magnetic sources. One leading hypothesis involves radical pairs. In certain light-sensitive molecules, a chemical reaction can create a pair of electrons whose spins are quantum correlated. The magnetic field can influence how the spin state evolves, which can change the probability of different chemical outcomes. Those chemical differences may then become part of a biological signal. The mechanism is compelling because it sits at the edge of detectability. Earth's magnetic field is weak, the cellular environment is busy, molecular reactions happen quickly. If radical pair chemistry contributes to magnetoreception, the organism must preserve or use a quantum-sensitive spin state long enough for a tiny magnetic influence to affect chemistry. The question is not whether the bird's mind communes with a field. The question is how a molecule could convert a quantum-sensitive spin process into a signal the nervous system can use. Quantum tunneling may also matter in biology and chemistry. In classical physics, a particle without enough energy cannot pass through an energy barrier. In quantum mechanics, there can be a non-zero probability of appearing on the other side. This is not a particle drilling a little hole through the barrier. It comes from the wave-like structure of the quantum state. Tunneling is well established in physics, and it can contribute to processes involving light particles such as electrons or protons. In enzymes, tunneling may help certain proton or electron transfers occur more efficiently than a purely classical barrier crossing picture would suggest. In smell, some hypotheses have considered whether molecular vibrations and tunneling could play a role in odor recognition, though that area remains debated and must be treated cautiously. The boundary is important. Quantum biology is strongest when it identifies a specific molecule, a specific quantum effect, a specific timescale, and a specific biological consequence. It becomes weak when it uses quantum language as a decorative name for complexity. The living world, therefore, does not erase decoherence, it works within it. Some quantum effects vanish too quickly to matter at biological scale. Others may be fast, local, or chemically coupled enough to influence function before the environment washes them away. The real question is always mechanical. What state is coherent? How long does it last? What environmental noise acts on it? What reaction or signal changes because of it? And how does the organism amplify that microscopic difference into useful behaviour? This same caution is even more necessary around claims of quantum consciousness. Proposals have been made suggesting that quantum processes might play a role in conscious experience, including models involving microtubules inside neurons. The best-known family of such ideas is controversial. It faces a demanding physical challenge. The brain is warm, wet, chemically active, and noisy. Long-lived quantum coherence would usually be expected to decohere quickly unless a specific protective mechanism exists. Strong claims about quantum consciousness should not be treated as established science. This does not mean the mind is uninteresting, or that attention has no physical power. It means the levels must not be confused. Conscious attention can change brain activity, perception, emotion, and bodily regulation because the brain is an active biological system. A person noticing a thought as a thought may change its effect. A person attending to breathing may alter autonomic conditions. Those are real mind-body mechanisms. They do not prove that consciousness collapses wave functions or controls quantum outcomes. Psychological observation and quantum measurement are different phenomena that share a word only at the surface. The distinction makes both subjects cleaner. In the laboratory, observation means physical interaction and record formation. In the mind, observation may mean attention, awareness, and regulation. The first concerns photons, detectors, amplitudes, and distinguishability. The second concerns neural activity, body state, memory, and behavior. Metaphors can cross between them if they are admitted as metaphors, but evidence cannot cross so easily. A similarity in language is not a mechanism. The quantum measurement problem is already deep enough without adding unsupported claims. A single photon still lands as one point. A protected apparatus still allows interference. A path detector still destroys the pattern. Entangled particles still produce correlations beyond classical local instructions. Decoherence still explains why ordinary objects behave classically. None of that requires the human mind to stand outside physics. The strangeness is not weaker because it is physical. It is stronger because it survives precision. At the same time, the presence of human observers is not irrelevant in the broader scientific sense. Humans build the questions. We design the slits, choose the detectors, set the polarizers, isolate the ions, cool the circuits, decide which data to compare, and describe the results in a shared language. We are not outside the universe, but we are parts of it that have learned how to arrange matter so that nature answers with numbers. That is a quieter kind of participation, and a more trustworthy one. A measurement begins as a physical contact, but science begins when records become communicable. One laboratory must be able to tell another what was done, the apparatus must be described, the settings must be specified, the statistics must be compared. Objectivity is built not from a few outside the world, but from a disciplined network of records inside the world. The photon's mark on a detector becomes a scientific fact because it can be placed within repeatable conditions and tested against a mathematical rule. That may be the most careful way to speak about quantum reality. It is not arbitrary, it is not fully classical, it is not dependent on personal belief, it is not completely settled in its interpretation. It is a world where some properties become definite through physical contexts, where probabilities are fundamental in the working theory, where information has mechanical consequences, and where the classical solidity of everyday life emerges from countless interactions with the environment. The room at night can still be trusted. The wall is not waiting for consciousness to create it. The floor will hold the body. The window will reflect the streetlight. The book will remain where it was placed, unless some ordinary force moves it. Quantum physics does not make daily life dissolve. It changes the physical picture beneath that stability. The firmness of the room is not the most primitive fact. It is a calm surface produced by many quantum contacts, many scattered photons, many molecular collisions, and many redundant records written into the environment. This is why the double-slit experiment remains so powerful after more than a century of quantum theory. It takes the world down to a level where those environmental records are carefully withheld. It lets a photon approach two alternatives without the usual storm of traces. It allows amplitudes to combine. Then it shows with a pattern of dots that the missing record matters. When the path is not known by the world, interference can appear. When the path is marked, the pattern changes. The result is not a metaphor, it is a measurement. The photon before the screen is therefore not a tiny bead with a secret path. It is not a thought. It is not a miniature version of a familiar object. It is a quantum system whose future records depend on the full arrangement of the encounter. When it lands, the detector does not reveal every possible account. It gives one event, one point, one fact. The pattern of many such facts carries the trace of the possibilities that were allowed to interfere before the record was made. There is a restraint in that claim that matters. Quantum mechanics does not hand us a final image of reality that everyone accepts. It gives us something less comfortable and more durable, a set of rules that work with extraordinary precision, a set of experiments that force classical intuition to yield, and a set of boundaries against careless speculation. It tells us that measurement is contact, not magic. It tells us that information is physical, not merely mental. It tells us that the classical world is stable, but not fundamental in the way it once seemed. The old mechanical dream imagined reality as a clockwork already complete in every detail, with measurement as the act of opening a small window and looking inside. Quantum physics replaces that with a quieter and more demanding picture. The world is not unfinished in the sense of being whimsical. It is unfinished in the classical sense until interactions define which records exist. The laws remain strict. The probabilities remain exact. The facts, when they appear, are shareable. But beneath them is not always a hidden classical path. Sometimes there is only a structure of possible outcomes waiting for the right physical question. And so the single point on the detector becomes a small, disciplined lesson in humility. It is solid enough to be recorded, repeated, and built into technology, yet it comes from a process that cannot be reduced to a tiny particle secretly choosing a slit. The point is real, but it is not the whole account. The pattern is real, but it is not made of visible waves on the screen. The measurement is real, but it is not a human spell. Between possibility and record, nature uses a language more exact than our images and more subtle than our habits. When the apparatus is switched off and the room becomes quiet again, the ordinary world returns without apology. The detector rests on the bench. The screen holds its marks. The air moves faintly around objects that seem as stable as they ever did. Nothing has vanished. What has changed is the depth of the word stable. The world we inhabit is firm not because its smallest parts obey the old picture, but because countless interactions continually turn fragile quantum relations into durable classical facts. In that calm surface, the question softens without disappearing. A photon can refuse a path until the world asks the question in a form that leaves a trace, and from those traces, one by one, our shared reality becomes visible.